this is my updated biweekly update with the new addendums as requested. So regarding progress from past, I implemented the antibody affinity maturation tutorial as outlined in the Modeling Immunity with Rosetta paper, and I applied it to the GD2 structure I obtained from OpenBabel and ChemDraw, made into 3D conformers with BCL, and I applied it to a docked structure of GD2 onto 6ZEC, which is a random fab structure I found in the PDB. I initially did the standard protein ligand docking, not glycan dock, using a docked pose that I randomly selected. I used that as an input to the affinity maturation protocol because the affinity maturation protocol needs to have a complex structure. But when I ran it, I got multiple errors in Rosetta. It did eventually finish, and the ligand also got processed in a strange way. I believe the Rosetta attempted to repack the ligand structure, which should only be done for peptides, not small molecules. And so, I mean, right now I've reached the conclusion, though not definitively, that Rosetta affinity maturation or single state design is really only capable of handling protein antigens, not ligands. And I have to use a separate protocol for ligands. And I did obtain designed structures, but the binding affinity was not improved, and the ligand in the output looked completely messed up. So something clearly went wrong within, and I'll show that in a later slide. So the exact tutorial I used was the one in Modeling Immunity with Rosetta, linked here in the supplement, and it's called the Single State Design Tutorial. And it's the same one used in the Woldring Lab workshop. And how I tweaked this to attempt to accommodate GD2 instead of a protein antigen. I specified natro in the res file. And the res file is a file within the protocol that basically you specify which residues you allow to be modified, to be mutated. All other residues are left alone. And natro is a specification that basically says, don't touch this, leave it alone, don't modify it. This residue, don't repack it either. Just leave it completely alone. And that's what I do for residue 235, which corresponded to GD2. And I know GD2 is not a residue, but that's the only way I could really incorporate it into the workflow. And here's a link for various res file specifications. And although I specified natro, the ligand was still processed incorrectly, as I'll show in a later slide. So the affinity maturation protocol generated 10 designed models and 10 control models. And the purpose of this was basically to show the difference between design and control, supposedly to show how the designed models both result in improved binding affinity to the ligand and in improved stability. It also aims to improve the stability of the binding site. So these res files specify which residues you allow to modify, and basically this is done manually. You look at the interface and you can specify as many residues as you like. You could say, oh, these are on the paratope-epitope interface. I'll modify these. I'll play around with these, and you specify whichever ones you want, really, on the specific chain that you want. In this case, they were all on the heavy chain, with the exception of 235, which was GD2. And in the design model, I put the ALA specification, which allows all 20 amino acids at these specified residues, and then Rosetta will make mutations from all 20 amino acids and assess which ones improve stability and binding affinity. In the control file, the difference was that I specified NADA, which doesn't modify those amino acids. It leaves them alone, but it does repack them. And I got this from the Woldring Lab tutorial. This was the standard res file they used, and the modification I made was I just changed the amino acids for my specific protein structure. So that was the control, and this is the design res file that actually caused the mutations. And these are some of the errors that I encountered. They were from the start sort of indicative that Rosetta in this specific protocol can't really handle non-peptide ligands. Missing heavy atom, also can't find pose, had a few others. And this was ultimately what gave in the fact that the affinity maturation protocol didn't handle the ligand properly. On the left is the output structure from standard protein ligand docking. I used the protocol that Ray and I worked on. I obtained a docked pose, and then I used this specific docked pose as an input to the design, to the single state design. And the ligand clearly, its structure was clearly altered, even though I specified natural, preserve input rotamer, and do not repack. Basically, leave it be. But this happened despite that. And the design did work, however. I obtained a few mutational changes. This is the design, and this is the control. And there's substitutions here. There's a few other substitutions, but these are the ones closest to the beginning of the sequence. And superimposing the design input and output. Again, the design input was basically the standard docked pose obtained from pre-Teleris 2014. You can see that the protein structure itself is very similar. The RMSD was actually 0 in Pimal. And the ligand structure is very clearly modified. Ligand structure has all these jagged edges, and it doesn't resemble any normal Pimal ligand structure. The design control and the design output, again, the protein's very similar, and in this case, the design control, since it also involved the affinity maturation protocol, the ligand was messed up in both cases, and it looked the same. So as soon as Rosetta attempts to touch the ligand and treat it as a residue, I believe it goes from being a normal structure to being this jumbled mess, no matter if it's a control or an actual design. So as is, definitely this protocol is not meant for ligands, carbohydrate ligands, or any non-peptide ligands. But I did obtain design results, namely an improvement in binding site stability score. So the designed score actually was, noticeably improved compared to the control score, in which the amino acids were unchanged. However, the binding energy was the same. I don't know if this is simply due to the fact that I only generated 10 models for both the control and the design. If I generated more, perhaps I would have seen a difference here too. But I only generated 10 so I could get results quickly and just to play around with it, see what I can do. So yeah, and I have a different protocol in mind that I want to try. It's called Rosetta and the design of ligand binding sites, so specifically for ligands, and I'll mention that in a later slide. But as is, the single state design tutorials seems to be meant for peptides. Okay, so I emailed both Rocco Moretti. He CC'd Dr. Elisa Martina, also from the Myler lab, on my email, but eventually they both said that they don't know anything really about glycan dock, and they can't really help me with that. And they suggested I contact the Gray lab, which I did over 2.5 weeks ago now. I'm still waiting for a reply. But I sent a short follow-up email to Rocco Moretti, specifically not about glycan dock, but rather about affinity maturation. And this is my follow-up email. Okay, so plans for future. I think I found a protocol that will work better. It has a book chapter. I put its DOI here. It's by Moretti, so that's why I sent the follow-up email, because I saw he does, although his expertise might not be in glycan dock, it definitely is in the relation of protein design in that realm. So I have hope in him as a source. And so this protocol, I have hope in it because it's specifically designed for ligands. It has all the typical Rosetta stuff that's for ligands, like params files, conformer generation. So it treats them as it should, not as residues. And I hope to combine this with GlycanDoc. So once GlycanDoc is implemented, I will do um, the design of ligand binding sites protocol to generate mutations. I'm hopeful that it will work for antibodies too with their, I mean, they are proteins after all, but they do have, I mean, this is me just going ad hoc here, but I'm a little afraid with all of their numerous loops and stuff that they might not be as susceptible to this as enzymes per se. I don't know, maybe their loop structures are different, but I have more hope in that in this protocol than in the single state design one. So this is a flow chart of really the computational side of the workflow that I aim to do. So once I obtain several sequences of mutationally and uh, mutationally optimized and humanized mutants, so they're stabilized in terms and they're also humanized to a great extent. Then I will perform standard docking of GD2 using pre-Talaris 2014. Then GlycanDoc will be performed to optimize the docked pose because GlycanDoc also needs an input of a docked complex. It only does local docking. Then I'll do the design of binding sites, hopefully using the new protocol. I'm really hopeful that it might work. Then, once the new mutations are generated using the Rosetta and design of ligand binding sites protocol, we will then verify that those mutations don't compromise the already established stability and humanness. Hopefully they won't. And then from those, the optimal sequences will be selected, and then library expression, which I hope to learn more about, but I currently am not knowledgeable of at all. Okay, so regarding the COVID manuscript, I was looking through Wiley journals because Wiley's the publisher that has the agreement with MSU to cover open access costs, which I mentioned previously in my past my past YouTube biweekly video. Feel free to reach out to me if you can't find it. It might have been lost in the ether, but I still have that link. So this is the link to the specific journal. It's called Molecular Informatics. I've seen several computational docking studies, purely computational, no wet lab. Its impact factor is like 3.3, and the caliber seemed pretty similar to what we've been doing. So I thought it might be accommodating of this type of work. And it's also pretty friendly based on what we already have. I mean, the only change I'd really need to implement is shorten the abstract even more, because even with 250 words, it surpasses 1,700 characters. So I need to get it down to 1,000 characters to meet the journal requirements. But that's really it. They also offer templates in which to like copy and paste all of your content, figures, text, everything, and I mean, they say it's recommended, not required, but I mean, you can basically see what it will look out in its what your manuscript will look like in its final form with the template. So I think that's pretty helpful. But I still think personally the most friendly journal, most accommodating, the one that contains the most similar studies is Journal of Biomolecular Structure and Dynamics. Um, it really has tons of computational docking articles. Like that actually looks like it's its main focus. And in terms of like manuscript submission, really no modifications need to be made. Like there's no new sections that they require. They don't need like a shorter abstract or a limit on the number of pages. Other journals that we considered, including Computers in Biology and Medicine, they have a page limit, which we exceed by a lot. So, yeah, I don't think it's really feasible to make the changes for that one, especially given that its impact factor is not much above these at all. So, yeah, this one's probably the one that it's most ready to submit to. Molecular Informatics is also really good. I liked the content. But ultimately, I'm not going to be the one making this decision. I'm just putting forth suggestions. So, yeah, and I found a list of specifications for biomolecular structure and dynamics. I mean, this stuff is all germane, but like 34% acceptance rate. I mean, I'm a little frightened about that, but other than that, I don't know. Given that the content in there is very similar to what we've done, I'm thinking they would be accommodating, and probably the acceptance rate is low because they might receive irrelevant content. I don't know. I'm hoping it will work out. All right, that's about all.